As you can see, the left graph shows the input and output relationship. In the right graph show the cost function. Here we have three data set with theta 1 equal to 1. Now we can calculate the value of cost function using this equation. For theta 1 equal to 1, we get the value of cost function equal to 0. Now we can plot the point into the cost function graph. Next, for the theta 1 equal to 0.5, we can see the gradient of the graph is reduced. Then we plug in into the value into the equation again. We get the value is equal to 0.58. Let's change again the value of theta 1 equal to 0. The graph will become like this. Then after we insert the value into the equation, we get the value of 2.333. When we increase the value of theta 1 to greater than 1, we can see the output of the cost function is like a mirror. At axis theta equal to 1, the cost function is concave. We can see clearly with 3D value j, theta 1 and theta 0. Thank you.
So my name is Ahmad Zaim and today I would like to explain about the gradient descent. So this is an example of contour figure of cost function J where the axes are theta 0 and theta 1 and the circle of eclipse represents the set point of value J, theta 0 and 1, and on the left is the training data set that we use to make our hypothesis. For this example, the function hash x is linear, and when we compare with the function J, the point quite close to the center of the contour. This is the minimum of cost function J. The point near at the center means that our function J is minimized, which is the aim of our hypothesis. It also means that the sum of square error between the training data and the hypothesis were acceptable. And algorithm gradient descent is used to minimizing the cost J. Based on the equation, we need to choose the value of alpha. And to see if gradient descent is working, print out the cost function of each iteration. The value should decrease at each iteration. If it does not, adjust the learning rate alpha. However, if the alpha is too small, gradient descent can be slow. This means the learning rate is slow to the minimum and will take a lot of steps. This is what we call as slow convergence. However, if the alpha is too large, the gradient descent can overshoot and may even fail to converge or diverge. If we take a huge step, the cost function has gotten worse as it had gotten further away from the minimum. This is what we call as overshoot.
Okay, my name is Ahmad Shahi and I would like to present about week 6 tutorial question number 1. Gradient descent and feature scaling for gradient descent. Feature scaling is a machine learning is one of the most critical step during the pre-processing of data before creating a machine learning model. It can make a difference between a weak machine learning model and a better one. The most common technique of feature scaling is normalization and standardization. For the normalization, it used when we want to bound our value between two numbers, while standardization transforms the data to have zero mean and a variance of 1. It makes the data unitless. So next, why do we need scaling features in machine learning? This is because machine learning algorithm just sees numbers. If there is a vast difference in the range, say few ranging in thousands and few ranging in tens, and it makes the underlying assumption that higher ranking number have superiority of some sort. So these more significant numbers start playing a more decisive role while training the model for machine learning. So that's all for me. Thank you.
Hi, my name is Anufaiz bin Azhar from Powerbank S2. Today I will discuss about the cost function. The use of cost function is to identify best fit of data and make good result for classification. And in this slide, we can see linear regression cost function have this formula, and it have two parts, which is y equal to 1 and y equal to 0. For the first example, if y equal to 1, it represents the negative log hx. In this graph, you can see the value starting in the hx. The starting point is 1 and the value of cost is higher. Cost equal to 0 if prediction is correct. For the opposite, as hx equal to 0, cost will be higher or infinity. Capture institution if h equal to 0 but y equal to 1. We will analyze the learning algorithm by a very larger. For the second example, which is y equal to 1 represent negative log 1 minus hx. In this graph, the line is the black line, which is the starting line at the 0 hx represent the y equal to 0, and then the value of cost is higher. For the opposite, as 1 minus hx equal to 1, cost will be higher. That means it's capture institution that larger mistakes should get larger penalties. Okay, that's all from me. Thank you.
So my name is Ahmad Zaim, and today I would like to explain the week 7 tutorial question number 2. So this is the question. So let's begin. Let's begin by explaining what is a cost function. Cost function is a function that measures the performance of the machine learning. And this is the example of the most popular cost function called a square error function. The aim is to minimize the j, theta 0 and theta 1 over here. So one of the problem with machine learning algorithm is the overfitting that will cause them to perform poorly. And regularization is the technique that would be able to reduce or minimize the overfitting problem. Let's take a look at the example of predicting housing price with linear regression. The aim is to predict the housing price as a function. Firstly, we can use a linear function to this data, and we could get the straight blue line into the data. However, this is not a good solution as the data set here is flattened out to the right and it does not fit the data set. We call this situation as underfitting or height bias. Next, we could also use the quadratic function to the data and we could get the curved blue line over here. And lastly, we could fit the first order polynomial to the data as we have 5 parameters 1, 2, 3, 4 and 5. With this algorithm, the blue line will pass all the data set and that seems to be the great solution. However, it looks complicated and complex as it failed to generalize new examples for another dataset. In addition, if we have more feature or data, it would become much harder to plot the data. And this problem is what we call as overfitting or height variance. To solve the overfitting problem, we can reduce the number of the feature. But if you want to keep all the features, we can reduce the magnitude or the parameter theta j. So I think that's all from me. Thank you.